All right, so in your warm-up, who has an idea how to simplify log 10 to the 6x? Yes, Yusuf? Something like that. So he wants to move it. He's on the right track. Where do you want to move it to? What are you talking about? Okay, so like that. Yusuf, is that what you were saying also? Okay.
And then we have the multiplication, then we have to separate them.
No, but something else does happen here. What is the base of this log? It's a 10, right? So isn't that log base 10 of 10? So what do we get to do with those? They get to cancel. Yeah, so it's just 6x. Do we remember why we get to do that? Besides, I told you so. Okay. Remember, logs are equal to exponents, right? So if you have something with the same base, okay, I'm just gonna make it like a 5. Okay, like this. This is saying the base of 5 is raised to what to stay 5? The exponent of 1, right? So this is the same thing as saying 6x times 1, because 10 raised to what stays 10? 1. Okay, that's called the identity property. Okay, so you have the same bases like that match up. They get to cancel out. What's up? So that's your common log. So when there is no base written, it's going to be a 10. Kind of like if we don't write an exponent, it's there, but it's just the number 1, right? It's the same kind of idea. Square roots, you put the little 2 out there, but we know it's there. Same kind of thing. All right, so keeping that in mind, how about part B? It cancels out again, and we get negative 0.2x. For the same reason, I can take my power, bring it out front. It ends up being 0.2x times 1, because natural log is a log with the base of e. So it's the same idea. Okay? So that's called the identity property, which is important because we're going to use it today to solve. Okay? So if you have a log, you bring a base to cancel it out. If you have a base, you bring a log to cancel it out. Okay? They're inverse properties. Like if I was multiplying by 2, I would divide by 2. Right? That would cancel it out. Same idea. What's up? Technically, yes. Because it says to simplify, so you're not done simplifying if you still have the natural log in the answer. Yep. Good questions. All right, so my front, we're going to simplify exponentials. The back, we will simplify and solve logarithms. Okay? So there are some little tips and tricks we can use. So solving exponential equations. Exponential equations are equations in which variable expressions occur as exponents. You can use the following property to solve some exponential equations. So if I have a base to an exponent equal to the same base raised to a different exponent, I can make my exponents equal to each other. Okay? As long as each side has the same base. Okay, or we can rewrite it as such. Like if I meant, like rewriting 25 as 5 squared, that's rewriting it. Okay, giving it a base and an exponent. Okay. First example, I have 6 equals 6 raised to the 2x minus 3. Okay, do they have the same base? Yes, so I can make my exponents equal to each other. What is my first exponent? Technically, what's over here on the left? What's the exponent to 6? 1. Okay, so I can make this 1 equals 2x minus 3 to solve for my x. So I don't have to bring in a log to get rid of my base if my base is already matched. All right, from here, what should we do? Add my 3, and then divide by 2. we get 2 equals x, like that. Okay. And you can always plug it back in to make sure you did it right. 2 times 2 is 4, minus 3 is 1, 1 equals 1. Okay, it works out. All right, part B over here. I have 2 bases, I have 2 exponents, but my bases right now are not the same. I have 100 and I have 1 over 10 as bases. Okay, but I could rewrite them as having a base to an exponent. How can I rewrite 100 to have a base raised to an exponent? 10 to the power of, what'd you say? 2. Do we agree with that same thing as 100? Okay. We still have the exponent of x here. So power to a power, this simplifies of 10 raised to the 2x. Okay. So my other side, I want to try and do that same thing, okay? I would like it to be a 10, so that way they can match each other. So how can I rewrite 1 over 10 as just 10 raised to an exponent? 10 raised to what? Negative 1. Nice. 10 to the negative 1 power is the same thing as 1 over 10. Exponent of x minus 3 is still here. Again, power to a power, we multiply. So this is 10 raised to the negative x and then plus 3. So this one had some rewriting, but now I have the same base. So now I can make my exponents equal to each other. So we get 2x equals negative x plus 3. All right, I'm going to add my x over here, divide both sides by 3. We get x equals 1. 2 times 1 is 2. My other side, negative 1 plus 3 is also 2. So we get 10 squared equals 10 squared. Yeah, cool. So it's nice when you can make them match. But what if you can't? Okay, like in letter C over here, I have 2 to the power of x equals 7. Okay, there's no way to rewrite these to have the same base. Okay, because 2 squared is 4, and then 2 cubed is 8. It totally skips over the 7, right? So I can't make a match. So when it's not convenient to rewrite each side of an exponential equation using the same base, you can try to solve the equation by taking a logarithm of each side. Okay? The logarithm we bring in has to match the base with our variable exponent. Okay? So is that going to be the base of 2 or the base of 7? The base of 2. 2 has the x. Okay? So 2 has the x. We're going to bring in a log base 2 to both sides. Okay? So log base 2. Log base 2 to both sides. My left side had 2x. My right side had 7. So log base 2 of 2 to the power of x equals log base 2 of 7. Okay? And this takes us back to our warm-up. See how I have log base 2 of 2? Those cancel. There's my identity property. So that side is now just x. My other side, it is a number. It's going to be a decimal, right? We already know it's in between 2 and 3 somewhere. Okay? You got options. You can type it into Desmos. You can type it into your handhelds by using the log base function. Okay? So you push math, go all the way to the bottom. If you see log base, we can use it. Okay? Not every calculator has this, so you could also, everybody can use change of base. Change of base would have been log 7 divided by log 2, like that. And you do get the same thing. Okay? So about 2.8, 2.81. Okay? Questions about the algebraic side of solving exponentials? All right. I got a word problem to go just with this, and then we'll go to the back and do logs. All right. All right. An important application of exponential equations is Newton's law of cooling. Okay? This law states that for a cooling substance with a initial temperature T sub 0, the temperature T, big T, after little t minutes, can be modeled by T equals T sub 0 minus TR times E raised to the negative R little t plus TR. TR is the surrounding temperature and R is the cooling rate of the substance. Did that just blink? Okay, making sure I'm not seeing things. All right, so what are we doing? We are cooking alicha, okay? It's an Ethiopian stew. When you take it off the stove, its temperature is 212 degrees, all right? So, Will, what part of my equation is 212? Which variable am I going to replace with it? Which one? There's lots of T's happening. T sub 0. Yes, this is my initial temperature. So when you first take it out of the oven, that is the temperature. Okay. So T sub 0 is 212. Okay. The room temperature is 70 degrees. Right? So Hayden, which variable is that one going to represent? The 70. Room temperature, the temperature surrounding you. TR, yes. Nope, you're good. You're good. So TR is 70 degrees. And the cooling rate of the stew is R equals 0.046. That was just nice and given to us. How long will it take to cool the stew to a serving temperature of 100 degrees? Yusuf, what's that 100 gonna? Which variable is that one? We have the big T left. Yes, big T. So which variable are we trying to solve for? Little t. Yes. How long will it take? So we're trying to find little t. Okay. I don't have something to plug in for my e, though. Did we miss something? Is e a variable? No, it is not. E is already a number, right? So we leave e alone. All right. So let's put things where they belong in our equation. So we're going to start off with 100 equals 212 minus 70 times e. What is happening? Okay, times e raised to negative r, so negative 0.046 little t, and then plus my room temperature again of 70. All right, so what we're trying to find is in the exponent, right? So we know we're going to have to bring in a log at some point, but I cannot do that until that e is by itself. Okay? So what do you want to move or put together first? Parentheses? Yeah? And then we could also subtract that 70 over at the same time. Is that okay if I do 2 and 1? So subtract 70 over, that gives me 30. 212 minus 70 gives me 142. 0.046 t. All right, my e is still not by itself, but it's still attached to it. The 142, so how are we going to get rid of it? Divide. So 30 divided by 142 is 0.211. Now we finally have that base by itself. Nothing else is being multiplied or added to it. Okay, so I can bring in a log with the matching base. What log has the matching base? Ln. Good, my natural log. So we're going to natural log both sides. Maybe. There we go. Natural log. There we go. Natural log. Okay. So those two cancel. Natural log of 0.211 gives me about negative 1.556. And my final step in getting little t by itself. Divide. Yes, let's divide by negative 0.046. And what do you get? Anybody? Will, what'd you get? Okay. Miles, same thing? Still typing it? Danny, is that what you got? 33.82? Okay, cool. So about 33.8, 33.82. Good. So let's answer the question. The question was, how long will it take to cool the stew to a serving temperature of 100 degrees? How long is it going to take? About 33.8 or 34 minutes. Yes. I wouldn't do 33 minutes because it's not cooled off yet, right? But does that make sense? Even if it was 33.2, at 33, it's not cooled off yet. Okay, so we're going to round up. So around 34 minutes. So word problems get word answers. Here we go. So you should wait about 34 minutes, or you can put 33.8 before serving that stew. How do we feel? So we solved exponentials using logs. Now we're going to flip-flop it. We're going to solve logs using exponentials and bases. Okay. All right. Solving logarithmic equations. Well, logarithmic equations are equations that involve one or more logarithms of variable expressions. So there's a variable in there somewhere. You can use the following property to solve some logarithmic equations. So before we had the property of equality for exponentials, you also have a property of equality for logs. Okay? If you have a log equals a log and they have the same base, we can do the same idea of getting our values equal to each other. So here I could just say, oh, well, x equals 7. Okay? Something we need to point out and pay attention to. My variables, b, x, and y, are positive and real numbers. Okay? Because what's the one thing, well, there's a couple things. What is something you cannot take a log of? You can't log. You can't do imaginary. You can't do negative, and you can't do 0. That's what that's reminding me. Okay? Has to be positive. 0 is not considered positive, right? It's not considered positive or negative. 0 is just 0. So it has to be positive and it has to be real. So when we get solutions, we're going to plug it back in just to make sure none of those happen. Okay, so I'm going to make sure that 4x minus 7, whatever answer I get for x, when I plug it back in, does not give me a 0, does not give me a negative, does not give me an imaginary. All right? We good? We ready? Let's do it. So part A, I have natural log 4x minus 7 equals natural log of x plus 5. Do I have a log equal a log? Yeah, I do. Do they have the same base? Yeah, they do. So I can, yeah, my natural logs essentially do cancel out. We get 4x minus 7 equals x plus 5. Now what? What do you want to do? Add the 7. Do you also want to subtract the x? So we get 3x equals 12. So x equals 4. Good. So again, we're just going to make sure that that 4 doesn't give me a 0, a negative, or an imaginary. So 4 times 4 is 16 minus 7 is, say 9. There you go. So that first one is natural log of 9. That's good. We like it. Other side, what is 4 plus 5? 9. So we get natural log 9 equals natural log 9. 9 is positive and real. We're good. Okay, so 4 is my answer. Remember, this usually becomes a problem when we have 2 answers, right? And then usually one of them doesn't work. Part B. I have log base 2 of 5x minus 17 equals 3. Do I have a log equal a log? Nope, I don't. I have just one log by itself on the other side, okay? So what can I bring in to cancel out that log? It's matching base, okay? What is the base of that log? 2. So we're going to bring in a base of 2 to both sides, okay? Like this. So this is 2 raised to log 2 5x minus 17 equals 2 raised to 3. Okay, those cancel. We get 5x minus 17 equals, don't say 6. What is that? That is 8. Good. That is 2 raised to the power of 3. Good. All right, now what? Add 17. And then divide. Here we go by 5. We get x equals 5. Let's double check. 5 times 5. 25. 25 minus 17 is 8. 8 is a positive real number. And isn't that true? Log base 2 of 8 is 3, so this is correct. All right. My next one says solving an equation with an extraneous solution. So it's giving you a little hint here. Something is not going to work. Okay? How do we usually get 2 answers, by the way? Yeah, we're coming from a quadratic. So something's going to happen here. Because notice this time, I have 2 logs, but are they equal to each other? No, they're together on the same side. So I'm going to condense them using yesterday's properties to make it just 1 log first. So if I'm adding 2 logs, what property do we get to use? The multiplication, the product. Good. So because we're adding, I'm going to multiply 2 times x and 2 times negative 5 to condense it into a single log. So this ends up being log of what? Mm-hmm. Beautiful. And we're still equal to 2 on this side. All right, so now it's like my last problem. I have 1 log by itself on one side. I have to bring in the base. What is the base of this log? 10. Good. This is my common log. So a base of 10 to both sides leaves me with 2x squared minus 10x equals, don't say 20, 100. Good. That is 10 squared. So here's that quadratic we were talking about. Okay, so get it all on the same side, make it equal to 0. Like this. So when it comes to solving quadratics, what should you always try and do first, if it's possible? Before that, factor out what? A 2, yeah, which is my GCF, right? If they can all be divided by something, let's do it. So these can all be divided by 2. I'm going to move up here. This gives me x squared minus 5x minus 50 equals 0. I'm not going to write the 2 because we're solving for x, right? 2 does not have an x. It's not going to help me. I don't need it. So, basic factoring here. Multiplies to give me negative 50. So I know it has to be a positive and a negative. That's how I know my signs already. But they have to also add to give me negative 5. Negative 10, positive 5. I agree. Which gives me x equals positive 10 and x equals negative 5. We have to test them, okay? I have 2 logs to plug it into. Messing up only one of them makes it not work for the entire equation, okay? So first let's plug it into 2x. What is 2 times 10? 20, that's fine, okay? Check the other one. We have log of x minus 5. So what's 10 minus 5? 5. So those are both fine, right? So I like 10. How about negative 5, though? What's 2 times negative 5? Negative 10. It already is bad, okay? But if you plug it into the next one first, log of negative 5 minus 5, that's also negative 10, right? So that's also bad. So this guy cannot do it. This is our extraneous solution. Okay? Because we ended up getting log, what was that, negative 20? No, it wasn't. It was negative 10. We ended up getting log of negative 10, which we cannot have. Yeah? So 9 times out of 10, if you have 2 answers, one of them probably isn't going to work. Okay? It works algebraically, but it does not follow the laws of logarithms. All right. Let's talk about some beetles. Oh, yeah, here we go. Scientists studying longhorn beetles in Florida use the model log S equals 0.9202 plus 0.2864 log A to approximate the number S of species on an island with an area of A square kilometers. Approximate the area of an island that is home to 20 species of longhorn beetles. Good times. So we're trying to find the area. So we're trying to find A. What we're trying to solve for. Okay. We're trying to get this guy by itself. Okay. So what do I get to plug in for S? 20. Yeah. 20 species. So 20 is my S. Okay. So we're going to have log 20 equals 0.9202 plus 0.2864 times log A. All right, with problems like this, we're going to try to wait to round until like the very end, if possible. So when I move things over to log 20, we're going to subtract first, right? Subtract the 0.9 and then divide by that 0.2. Okay, so let me show you something. So log 20 minus 0.9202 all over 0.2864. All right, and I'm going to use my calculator to figure out the most exact solution to this. Okay, some of you know this trick, some of you don't, so I'm going to make sure just everyone knows how. Okay, so calculators. Okay. So we have log 20, close your parentheses, minus 0.9202. Okay, we get that lovely decimal. Okay, I'm not going to round it. I'm not going to retype it. What I can do is say, okay, I want to take that and I want to divide it. See how it says ANS? It's taking your answer. Okay, I'm going to divide it by the 0.2864, like that. And then I can round that to about 1.33-ish. Okay? So some of you knew this, some of you did not. Now we all do. Okay? You can also do second and then the negative sign to also get your previous answer. The ANS is in blue. That's what that means. Yeah, fun stuff. Okay? All right, we're not done yet. That's not my answer though, right? So I have 1.33 equals log A. I need A by itself. Now I have a log attached to it. What do I have to bring in to cancel out that log? A base of 10. Good. We got to bring in a base of 10 because that's a common log. So base of 10 to both sides. So we get 10 raised to 1.33, which is about what? 21 point what? 36. So to answer the question, because it wants to know approximate the area of an island. So the area of our island is about what?
22 kilometers.
About 22 kilometers squared, or you can say about 21.36, 21.4. Lots of ways to answer this one. Here are mine. The area of the island is about 21.4 square kilometers with its 20 species of longhorn beetles. Mm-hmm. All right, any questions about anything from today? All right, sweet.